whenever
Okay,
you
thanks
are
a
ready.
lot. Thanks a lot. I'm going to spend the next few minutes discussing about advertising even. The ROCKE-3D version 2 that we have been developing for the last few years. This is a major effort that includes a lot of people that I want to acknowledge here. We have a paper in preparation and we're very excited about this new release. So this is ROCKE-3D is the evolution of ROCKE-3D version 1, which was published in 2017. And I will have a few links in my presentation. I will be going quickly through them, but you will be getting the presentation later, so don't worry about that if you cannot write down whatever you want as a reference material. So we have been updating that model for a number of years now, and this is what we're going to be releasing. The ROCKE-3D version 1 has a lot of resources, like how to install the necessary compilers and libraries on your local computer, how to install the actual model. We have tutorial slides and tutorial videos that we run annually, and we welcome people. So if you want to participate in this upcoming May tutorial, feel free to contact me by email. Make sure you check the tutorial slides because this details exactly which model, which cases you can run and which cases you cannot run with this model. I'll give you a hint. ROCKE-3D can only simulate rocky planets, and it needs an atmosphere to simulate its climate because otherwise it makes no sense. So, but there are more fine information that you can find in there. Then the ROCKE-3D version 1 code is available. It is not in EMAC available, and the reason is pretty obvious. You cannot just download the code and run it. It's not as simple as running some smaller set of codes. We're talking about a 500,000 line model, so it's pretty intense. So that's why we're having also annual tutorials about that. The model has some the limitations that it has, so it resolves the whole atmosphere in 3 dimensions and also the ocean. And in case the planet has a terrestrial biosphere, it also has that. It can simulate up to maybe 10,000 years, and the reason is not that it cannot simulate more. The reason is that it is a slow model, so you will have to wait very, very long times if you want to go beyond like 10,000 years. The vertical resolution goes up to 65 kilometers, so we cannot simulate escape, we cannot go that high up. And then we are limited in shallow atmospheres. So nothing like mini Neptunes or even gas giants. And even for the super Earths, we have some limits that we might hit here and there. But for planets like comparable to Earth, maybe 30% bigger, maybe smaller, like Mars size or even smaller, we're probably okay. The new things in ROCKE-3D involve numerous physics and parameterizations updates, more supported configurations, geothermal heat flux, support for thinner atmospheres. We can go up to millibar, up to some tens of microbars even, I think, surface pressures, improved present-day Mars, and also support for deeper oceans, which is not final. It might not be available for 2.0, but it will be for some future version. And in this presentation, I will only focus on the blue line here, the support of the different configurations. And since the audience here is mostly interested about the technicalities of the code itself, rather than showing off, a random set of results, I decided to make this talk a little bit more technical because it will help you understand how to actually use the model. So there are a number of configurations here that you can use. We have this way to name it, as you can see at the very top. I will explain it right away. In general, P2 means this is the Planet 2 version of the model. And then we have 2 different flavors of radiation, the GISS radiation, which is the one that is coming from the heritage of the model, and it is very fast and very good for atmospheres that resemble present-day Earth. And then we have the Socrates radiation, which is slower, but it has more capabilities in what you can actually simulate. Then we have 3 flavors of the atmosphere. One is the atmosphere of pre-industrial Earth, exactly as described by the parent GISS model E model. and it is simulating the year 1850 or later if you want. Then we have the version that we call X, and this is the same atmosphere as it was simulated for Planet 1.0, and that does not have aerosols, it does not have ozone, it does not have stratospheric water formation from methane oxidation, but it does have molecular oxygen and argon. So that was a little inconsistent, and we decided we will introduce here the atmosphere we call N for anoxic, and that will be the same as X, but with no molecular oxygen and argon. So essentially it is 100% nitrogen atmosphere except the trace gases that it holds. Then we have three different versions of the atmosphere, of the ocean. One is a prescribed 1880 sea surface temperature and sea ice extent. That's a standard thing that people that only care about the atmosphere do for Earth simulations. You can replace it with any data set you want if you want to create a new one. We have a Q-flux ocean, which is a mixed layer or a mixed layer depth ocean, 100 meters depth, deep. You can play with this number, and it has zero heat transport between across latitudes or longitudes. And this is different from what we had in Planet 1.0. And then we have a dynamic ocean. It goes all the way to the ocean bottom, and it resolves everything that you want to resolve. The resolution of the model is either the fine resolution, which is 2 by 2.5 in the atmosphere, 40 layers, and 1 by 1.25, 40 layers for the ocean, or the resolution that we were mostly using for the Planet 1 version, which is the medium resolution. It is 4 by 5 in the atmosphere and also 4 by 5 in the ocean. So we are supporting all possible combinations of the cases you see here. And one of the things that we say is that we prefer to use the Socrates radiation, anoxic atmosphere, dynamic ocean, and then you can pick your resolution. So performance changes quite a lot when it comes to the different configurations, and you see all the different models at the bottom, and at the top you see GISS, Socrates, the same letters essentially. So with red colors, you see the final resolution, and with the blue, the coarse, and you see that this is a quite big difference. Then if you see the left half of the plot is the GISS radiation, and the right half of the plot is the Socrates radiation. And in particular with the coarse model resolution, the blue lines, you see that it is much more expensive than the GISS ocean, the GISS radiation. And then there are more fine information here that you might want to see. But the dynamic ocean also for the GISS radiation you see is more expensive than the prescribed, which has no ocean practically, or the Q-flux. And this is not so noticeable in the Socrates case because the Socrates radiation takes up much time by itself. An important thing for any simulation one does is that you need to have the net radiation of the model, the net radiation of the planet being in balance. So whatever comes in goes out. So the planet is in equilibrium. And we have this generic threshold that it is if you are within 0.2 watts per meter square, either negative or positive, you're pretty good to go. But what I'm showing you here is that for every simulation, you get a quite significant amount of scatter in the values you get if you look at the individual years that you simulate. So you need to really sample over multiple orbits of any planet to confirm that you are really in radiative balance. So the mean over multiple orbits needs to be within 0.2 or a little bit more if you have a very weird planetary configuration. Then the equilibration times differ as well depending on the configuration that you have. The prescribed ocean equilibrates extremely quickly. So at the top row here, you see the net radiation of the planet, which needs to be approximately close to 0 or around 0.2. And at the bottom, you see the global mean surface air temperature. And you see that for both cases here, which is the fine resolution with blue, the coarse resolution with red, and the planet 1.0 with green, you see that it equilibrates pretty quickly. For the Q-flux ocean, planet 1.0 equilibrated much faster. You see it only takes like a couple of decades to go into near zero here, and the temperature will equilibrate. For the planet 2 version, for the version 2 of ROCKE-3D, this takes much longer, maybe even 100 years. And also the temperatures are much colder. And the reason is that we are using a zero Q-flux ocean, so no heat transport happens inside the ocean, which is different from what we had in planet 1.0, that we were using the Earth's heat transport. And we chose to use zero right now because for any other planet, we will never know the actual amount to use, the actual value to use. And also zero is something that that is very common in other simulations, in other modeling centers or other planets, or including ours. And then we have the dynamic ocean that you see takes at least a millennium, maybe near 2 millennia for equilibration. The planet 1.0, the ROCKE-3D 1.0 equilibrates at about 1,000 years. For the medium resolution of the version 2, it takes at least 1,500 years. So these are important things to know when you're designing your own simulation. This is a quick look of several key diagnostics, and I will only guide you through that very quickly. So I have the simulations at the bottom, and I am only comparing against the very last one, which is the recommended one. So if it is white, then the simulation looks very much like this last one. And obviously the whole column at the very end is white because you are comparing against yourself. And then everything that is dark red means at least double. Everything that is dark blue means at least half. And so you compare a number of different diagnostics here. So what stands out is that for this block here, which is the Q-flux ocean, and that block here, which is again the Q-flux ocean, there are some major differences, actually some strong increases in everything that is related with ice. So snowfall, snow fraction, snow depth, ocean ice fraction, and the ground albedo, everything increases by a lot. And the reason is that we are using a zero Q-flux, so everything is much colder, and everything, including albedo, increases. Then the temperature is dark blue here and also dark blue there. So you see the same thing, that it's a colder planet. You can see that for the case of planet 1.0, which is in the first 6 columns, the high clouds are much higher than anything in the planet 2 version. And I can keep up spending the whole presentation here in that plot, but I'm going to leave it to here, and you will find in the paper much more discussions about it. Again, this is the surface temperature, global mean surface temperature on the left, and the ocean ice fraction on the right for all the simulations. And you see essentially the same thing in a different way. That includes a little bit of the variability. The Q-flux ocean is having here and here is colder, and that gives you higher ice fractions that reach even exceed 30%. And the difference between this column and that column is the radiation. And then you can also see here that there is something like a step going down, up, down, up, down, up. This is related with the resolution of the model. So this is fine, coarse, fine, coarse, fine, coarse. And that is a pattern that you see nearly everywhere. And
I know we have the break later. Maybe can you wrap up? Because
yes, I will wrap up in a slide. And thank you. So we will, and then these are important things that you need to take into account for your simulation. In the vertical, there are also major changes. The important thing is that when you take away ozone, temperature drops by a lot, and that takes away also relative humidity. And these are also things that are expected, and nice to see that the model is simulating. And I'll stop here. The code is going to be released in a few months, and I'm happy to take questions on Slack probably because I ran out of time. Thank you.
No worries. It's fine. It's the last talk until the break. maybe you can take one question I see in the chat. So thank you for the amazing talk. Could you talk a little bit about photochemistry, and does the code include photochemistry? And if so, in which regimes is it valid for?
So the answer is yes and no. So it does include photochemistry. We have right now present day Earth, and we can simulate up to, we can also take away some oxygen and go down to maybe 10 to the minus 5 present day levels. And if this is the only change we make, we can assume that this works. We are still finalizing certain things. So for the version we'll be releasing, photochemistry will be included there, but it is not recommended to use for outside present day Earth yet. So it will be in a next release or an additional, also in another paper that we will be discussing about prognostic atmospheric composition. So everything I described here is prescribed atmospheric composition.